Hey kids, Smath here. Got one of our later, if not final installments on thermochemistry. This is Hess's law. All right, Hess's law of heat summation, to be exact with you. And the deal with Hess's law is it basically says the energy of a chemical reaction can be found indirectly by summing up elementary reactions. That sounds kind of confusing to me. I don't understand. It's a fancy way of saying, well, basically the overall energy can be found by summing up the energy of the individual parts. So in this case, why would we ever want to do that? Well, the overall reaction may be too dangerous. Maybe you want to find out how much energy is given off by nitroglycerin or dynamite. Hey, how much energy is given off by igniting this dynamite? That's a little bit heavy. We may want to use parts of the reaction to kind of estimate the overall energy of the reaction. And we may not just be able to measure it. It may happen too quickly. So instead, we use the parts to equal the whole. So our question, to put it simply, is chemical reactions can be mathematically manipulated. If we manipulate the reaction, all we're going to do is manipulate the energy that goes along with that reaction. And so in this case, we want to calculate delta H for the following reaction. Lead chloride plus another chlorine is going to create lead 4 chloride. I call that my target reaction because that's the reaction we're trying to hit. We're trying to achieve the energy associated with that reaction given these two reactions. Those are called my elementary steps. So I have lead plus 2Cl2 makes PbCl4. My enthalpy for that, negative 393. And then I have lead plus Cl2 makes PbCl2. Okay, enthalpy of that, negative 359. Now, here's the deal with Hess's law. You can do anything you want mathematically to those two elementary reactions. You can double them. If you double them, fine. Put double coefficients out in front of everything and then double the energy. You could cut them in half. Cut the coefficients in half. Just make sure you cut the energy in half. Whatever you do to the chemical equation, make sure you do that to the energy at the end. And so in this first case, I see PbCl4 as a product. And I want PbCl4 as a product, so I'm going to leave that first reaction alone. Now, why did I pick PbCl4? Because both of these elementary reactions have Pb and Cl2, Pb and Cl2. That's a mess. There's Pb's and Cl's all over the place. So let's pick the things in the reaction, pick the species that are unique to that reaction. So PbCl4 is unique. I want it to be a product. I leave it as a product. Now, what about the bottom reaction? I have PbCl2. That's unique. I have it as a product. I would really like it to be a reactant. How come? Because it's a reactant in my target equation. So when it's a reactant in my target, I take the second equation, I write reverse. Some people don't write reverse out here, and instead, another fancy way you could do this is just say -1. -1 is the same thing as reversing a reaction, right? I think so. So when I reverse the reaction, now the Pb and the Cl2, they go over to the product side. The PbCl2 comes over to the reactant side. And what used to be a negative 359 now becomes a positive 359. Okay? Now the part that's kind of fun. If we do this correctly, and you have the same thing on both sides of the equation like we do here, lead on the left side, a lead on the right side. Well, I can cancel that. I have 2 Cl2s and 1 Cl2. So that one Cl2 is going to cancel, and that 2 is going to become a 1. And so watch what happens as we cancel out here is, thank you, the Pb cancels out with that Pb. So it's gone. And now this Cl2 is gone. And instead of having 2 Cl2s over here, now I only have 1. And it's called Hess's law of heat summation. So that when I add the reactions together, I should get the target. So bring the PbCl2 plus Cl2 makes Cl4. And if I add a negative 393 and a positive 359, I'm going to get a negative 34 kilojoules. And that's my answer. What was the energy of this as my target reaction? Negative 34 kilojoules. So we can manipulate equations and manipulate energies and calculate delta H. Let's look at our second example down at the bottom here. It says, calculate the energy, calculate delta H for the following. I take methane gas and chlorine, and I'm going to tack on a couple of chlorines onto that CH4. Boot out a little bit of hydrogen, make some hydrogen chloride. This would clearly be one of those reactions that's too dangerous for us to be doing in the laboratory. We don't want to generate HCl gas. So let's calculate it here. And this one looks pretty complex because what they've done, they've given us a nice looking target equation right here. There's my target. And down below here, they've given us not one, not two, not one, not two, but 3 elementary steps. Elementary. Those are the ones that we get to manipulate and do anything we want to. So now let's blow it up so we can see it as best we can. And so we want, and sometimes you have to pick the one that's easiest to see. I look at the top one. CH4 is very unique. This is the only reaction that offers me this CH4 molecule. I have 1, there's a 1 coefficient. I need 1. So the first reaction is going to get reversed. Okay, doing that right out here. Reverse that reaction. The second equation, I have this CHCl3. Okay, trichloromethane is what that's called. That is a product in my target. It's a product in my elementary. So let's leave it alone. Don't mess with that equation. What about our third reaction? I got hydrogens and chlorines and halves. Oh, this is ugly. I've got to get rid of these halves and I got to get that hydrogen chloride. Okay, well, it's a product. That's the good news. But my target reaction says I need 3 of them and I only have 1. So I'm going to multiply that reaction by 3. Put a little 3x out there to the edge. So if I reverse the first, leave the second, and multiply the third, I get my answer down here. The first reaction gets reversed, rewrite it, and change a negative 74 to a positive 74. The second one I leave the same, I just rewrite it. And the third one, I multiply it by 3, so 1/2 times 3 is equal to 3 halves. 1/2 times 3 is equal to 3 halves, and 1 is equal to 3, and 3 times 92 negative is negative 276. Let's make sure everything cancels out, okay? Grab a different color pen here. I have 1 carbon and 1 carbon. They cancel out nicely. Okay, now the rest of it gets kind of weird. I have 3/2 of hydrogen there and 1/2 of hydrogen there. That makes 4/2 of hydrogen. That's 2 hydrogen molecules. And there they are. So that's going to cancel. That's going to cancel. Now notice I make different shapes for the different things that I cancel out. My carbons, I just put a hash through. My hydrogens, I put a circle and a hash through. If I had to cancel out anything else, I might use an X. I might use a star. I just use different shapes to show that I'm canceling things out. My chlorines in this case, they end up adding up. So what I have is 3/2 and 3/2, which equals 3. So my methane falls down, my 3 chlorines fall down, my trichloromethane falls down, and my 3 HCl's fall down. And when I do this properly, I end up getting 333 negative kilojoules. These are kilojoules that are going to be given off. So not only is this reaction going to generate hydrogen chloride gas, which we'd rather not be exposed to, but it's also generating a great deal of energy. So basically, Hess's law says we can manipulate chemical equations, and in doing so, manipulate the energies that's involved and calculate the delta H for different reactions by estimating elementary steps. I'm Smath. I hope this video helped you.